Voyager has been traveling through space for nearly half a century, far beyond the planets and the Sun. But one day, its power will fade, its signal will fall silent, and humanity's most distant messenger will finally die. How will that happen, and where will Voyager be when it goes dark? What Voyager really is. Voyager is not a robot with a mind, and it is not a machine that makes choices. It is a carefully built object, designed by people who never expected it to live this long, sent into space with no ability to change its fate once it left Earth. Everything Voyager does today is the result of decisions made in the early 1970s, when computers filled rooms, when memory was counted in kilobytes, and when nobody knew if a spacecraft could survive the cold and radiation far beyond the planets. To understand how Voyager will die, you first have to understand exactly what Voyager is, how it was built, and what it was never meant to be. Voyager exists as two spacecraft, Voyager 1 and Voyager 2, launched weeks apart in 1977. They are often spoken about as if they are twins, but they are better understood as two copies of the same design, sent on different paths through the solar system. They were not created to explore deep space forever. They were created to take advantage of a rare alignment of the outer planets, an alignment that allowed a spacecraft to move from one planet to the next using gravity alone. This alignment happens roughly once every 176 years, and the engineers who planned Voyager knew they had one chance to use it. If Voyager failed, there would not be another opportunity like this for generations. The spacecraft were designed with a very clear goal: fly past Jupiter, then Saturn, and if everything still worked, possibly Uranus and Neptune. The expected mission length was 5 years. That was it. 5 years was considered ambitious. Anything beyond that was a bonus. Every system, every wire, every piece of hardware was designed with that time frame in mind. There was no expectation that Voyager would still be operating in the 21st century, let alone sending data from beyond the edge of the Sun's influence. Voyager was built as a long, thin structure, dominated by a large dish antenna that measures about 3.7 meters across. This antenna is not decorative. It is the most important part of the spacecraft. Everything Voyager does depends on that dish staying pointed toward Earth. The antenna sends and receives radio signals, carrying commands from Earth and returning data from the instruments. Voyager cannot turn freely like a modern satellite. It rotates slowly, using small thrusters to keep its antenna locked on a tiny point in the sky where Earth exists as a faint dot. Behind the antenna sits the main body of the spacecraft, a box-like structure that holds the computers, power systems, and scientific instruments. Long booms extend outward, holding sensors far away from the spacecraft's electronics so that their measurements are not disturbed by electrical noise. These booms make Voyager look fragile, like a structure that could snap apart, but they are rigid and carefully balanced. Every part of the spacecraft was designed to survive violent launch forces, extreme heat near the Sun, and extreme cold far from it. One of the most important things to understand about Voyager is what it does not have. Voyager has no onboard artificial intelligence. It does not think, learn, or adapt. Every action Voyager takes follows instructions written decades ago, stored in memory that is tiny by modern standards. Voyager cannot decide to save power. It cannot decide to shut down a failing instrument. It cannot notice a problem and fix it. If something goes wrong, Voyager will continue doing whatever it was doing, even if that behavior slowly destroys it. Voyager also has no ability to repair itself. There are no spare parts, no robotic arms, no backup systems that can rebuild damaged components. If a circuit fails, it fails forever. If a sensor stops responding, it will never come back. Engineers on Earth can send new commands, but those commands can only tell Voyager to use systems that still exist and still function. Voyager cannot replace a broken wire or clean dust from a sensor. Its survival depends entirely on the original quality of its construction and the careful management of its remaining systems. Another limitation built into Voyager is the complete lack of propulsion for long-term travel. Voyager does not have engines that can push it through space at will. After launch, it used small thrusters for orientation, not for speed. The immense distances Voyager has traveled were achieved almost entirely through gravity assists. As Voyager passed close to a planet, the planet's gravity bent Voyager's path and increased its speed. This process allowed Voyager to move from one planet to the next without burning fuel. But once the last flyby was complete, Voyager was set on a fixed path. There is no turning back. There is no slowing down. There is no course correction that can change its ultimate direction in a meaningful way. This design choice was intentional. Carrying fuel adds mass, and mass makes launches harder and more expensive. In the 1970s, engineers worked under strict weight limits. Every kilogram mattered. Adding fuel tanks large enough for long-term propulsion would have reduced the number of instruments Voyager could carry, or made the mission impossible to launch with available rockets. So Voyager was built to coast, not to drive. Once it left the planets behind, it became a passive traveler, moving only because it already had momentum. At the heart of Voyager's ability to function is its power system. Voyager does not use solar panels. Far beyond the orbit of Jupiter, sunlight is too weak to generate enough power for instruments and communication. Instead, Voyager is powered by radioisotope thermoelectric generators, known as RTGs. These devices do not generate power through motion or chemical reactions. They generate power from heat, and that heat comes from the natural decay of a radioactive material. Each Voyager spacecraft was launched with 3 RTGs mounted on a boom extending away from the main body. Inside each RTG is plutonium-238, a radioactive isotope that releases heat as it decays. This heat is converted into electricity using thermocouples, devices that generate electric current when there is a temperature difference between two materials. There are no moving parts in an RTG. Nothing spins, nothing burns, nothing flows. As long as the plutonium continues to decay, the RTG produces heat, and as long as there is a temperature difference, electricity is generated. At launch, Voyager's RTGs produced roughly 470 watts of electrical power. That may not sound like much, but it was enough to run the spacecraft's systems and instruments. Over time, however, the power output steadily decreases. Plutonium-238 has a half-life of about 87.7 years, which means that every year, the amount of heat produced drops slightly. This decline is slow but relentless. Voyager loses a few watts of power each year, and that loss can never be reversed. The RTGs also serve another critical function. They provide heat. Space is extremely cold, and without heat, Voyager's electronics would freeze and stop working. The warmth from the RTGs is distributed through the spacecraft, keeping systems within operating temperatures. This means that power and heat are deeply linked. When power drops, heat drops as well, and systems that rely on warmth begin to fail, even if they still receive electricity. From the very beginning, engineers knew that power would be the limiting factor in Voyager's life. They knew that instruments would eventually have to be turned off to preserve power for communication. What they did not know was how slowly Voyager's systems would degrade, or how far beyond their expected limits they could operate. Many components on Voyager are now running at temperatures and power levels that were never tested on Earth. They are surviving not because they were designed to, but because the laws of physics allow them to keep going just a little longer. Voyager's computers are a perfect example of this. Each spacecraft has multiple computer systems, each responsible for different tasks. These computers use extremely simple processors, operating at speeds that are tiny compared to modern devices. Memory is limited, and programs are stored on magnetic tape recorders and early digital memory units. There is no operating system in the modern sense. Everything Voyager does follows rigid sequences of commands. These computers were built to withstand radiation, but only to a point. Beyond the heliosphere, Voyager is exposed to galactic cosmic rays, high-energy particles that can damage electronics. Over time, these particles flip bits in memory, causing errors. Engineers on Earth have learned how to detect and correct some of these errors, sending new commands that work around damaged areas of memory. This is not repair, it is adaptation from afar, using ingenuity to stretch the life of systems that were never meant to endure this environment. Voyager's design reflects the engineering mindset of its time. Redundancy was used carefully, not excessively. Some systems have backups, others do not. Instruments were chosen based on the science questions of the 1970s, not on what might be discovered in interstellar space decades later. Yet those same instruments are now providing data that no one anticipated when Voyager was built. What makes Voyager remarkable is not that it was perfect, but that it was robust enough to survive far beyond its intended mission. Its simplicity is part of its strength. Fewer systems mean fewer points of failure. No moving parts in the power system mean less wear. A fixed trajectory means no fuel exhaustion from constant maneuvering. These choices, driven by necessity and limitation, created a spacecraft that could endure. Voyager is not alive in any meaningful sense. It does not struggle to survive. It does not know it is aging. It simply continues to operate step by step, command by command, until the physics that sustain it finally fail. Every bit of data it sends today comes from hardware that has been operating continuously since the Carter administration. Every signal received on Earth is the result of electrons flowing through circuits older than many of the engineers now working to keep them alive. Understanding Voyager's mission architecture is essential because it defines how Voyager will end. A spacecraft with no self-repair, no propulsion, no intelligence, and a steadily weakening power source can only fail in certain ways. Its death will not be dramatic. It will not be sudden. It will be a gradual narrowing of capability, driven by power loss and environmental damage, until nothing remains that can speak to Earth. Voyager was built to observe, not to endure forever. It was built to pass through the outer planets and then fade into silence. The fact that it has not yet done so is not a miracle. It is the result of careful engineering, conservative design, and a deep understanding of physics. Those same factors now define the limits of its remaining life, limits that were set the moment Voyager left Earth and began its long, irreversible journey into the dark. A machine that cannot think, heal, Oregon, turn back. Voyager is often talked about as if it is clever, as if it is aware of where it is or what it is doing. But that idea collapses the moment you look closely at how the spacecraft actually works. Voyager does not think. It does not watch space go by. It does not react. Voyager follows instructions written decades ago, and it follows them blindly. Every move it makes today was either planned long ago or carefully sent from Earth in the form of radio commands that take more than a day to arrive. If those commands stop, Voyager does nothing new ever again. Inside Voyager is no artificial intelligence, no decision-making system, no software that can learn from mistakes or adjust to new conditions. The computers on board Voyager are simple, rigid, and unforgiving. They execute commands in a fixed order. If a command leads to trouble, Voyager does not question it. If a sensor gives strange data, Voyager does not investigate. It records the numbers and sends them home. That is all. The computers on board Voyager were designed in the early 1970s, when digital technology was still young. These machines operate at speeds that would feel painfully slow today. Their memory is tiny, so small that even a basic modern photo could not fit inside it. Voyager does not have an operating system in the way modern devices do. Instead, it runs sequences, step after step, like a long checklist that never ends unless Earth tells it to change. This matters because Voyager cannot save itself. If something begins to fail, Voyager cannot decide to shut it down. If power becomes dangerously low, Voyager cannot prioritize one system over another on its own. Every choice must come from Earth, and Earth can only react to what Voyager manages to tell it. If Voyager loses the ability to communicate clearly, there is no backup brain on board that can take over. Silence means total loss of control. This design was not a mistake, it was a necessity. In the 1970s, computers were heavy, power-hungry, and fragile. Adding complex onboard decision systems would have increased weight, power use, and risk. Engineers chose reliability over flexibility. They chose predictable behavior over intelligence. Voyager was meant to be obedient, not clever. Voyager also cannot fix itself. There are no robotic arms tucked away inside the spacecraft. There are no spare circuits waiting to be swapped in. There are no systems that can isolate damage and rebuild around it. If a wire cracks from decades of cold, it stays cracked. If radiation damages a chip, that chip is damaged forever. Engineers on Earth can only work around problems, not remove them. When Voyager experiences a fault, it does not diagnose itself. It may switch to a backup system if one exists, but only because that behavior was pre-programmed long ago. Many parts of Voyager have no backups at all. They were never expected to need them. When those parts fail, they take their function with them permanently. Over the years, Voyager has suffered many of these small losses. Some instruments stopped responding. Some heaters failed. Some memory locations became unreliable. Each time, engineers adjusted commands, shifting workloads, rewriting code, and finding creative ways to keep the spacecraft alive. But these fixes are fragile. They rely on Voyager still being able to listen, respond, and follow orders. If that chain breaks, nothing on board can restore it. Voyager also has no way to help itself if its orientation fails. The spacecraft must keep its antenna pointed precisely toward Earth. This is not optional. Even a small misalignment can weaken the signal so much that Earth can no longer hear it. Voyager uses small thrusters to adjust its orientation, firing short bursts to correct its aim. These thrusters rely on fuel lines, valves, and pressure systems that are now nearly half a century old. If a thruster sticks, leaks, or freezes, Voyager cannot compensate on its own. It cannot choose a new strategy. It cannot decide to reduce movement to conserve fuel. It will continue following its last set of instructions until those instructions become harmful. Earth can send new commands, but only if Voyager can still receive them, and only if engineers notice the problem in time. Another critical limitation is propulsion. Voyager does not have engines that allow it to change direction in any meaningful way. Once it finished its planetary flybys, its path through space became fixed. The speed and direction Voyager has today are the result of gravity, not choice. It is moving because it was pushed long ago, and it will keep moving whether it is alive or dead. This means Voyager cannot avoid danger. If it passes through a region of higher radiation, it cannot steer away. If it encounters interstellar dust at high speed, it cannot slow down. If its trajectory slowly changes due to gravitational forces from distant stars, Voyager cannot correct it. It is a passenger, not a pilot. The lack of propulsion also means Voyager cannot return. There is no scenario where Voyager turns around. There is no fuel reserve waiting to be used. Even if Earth wanted Voyager to come back, physics would not allow it. Voyager crossed a point of no return decades ago. From that moment on, every kilometer carried it farther from home. These limitations shape everything about Voyager's present and future. The spacecraft exists in a delicate balance. It must keep communicating, keep pointing its antenna, keep its systems warm enough to function, and keep its remaining instruments alive. It does all of this without awareness, without adaptation, and without the ability to save itself if something goes wrong. What makes this more intense is the distance. Voyager is now so far away that signals take over 20 hours to travel one way. When engineers send a command, they wait almost 2 days to see the result. If something goes wrong, there is no quick fix. There is no emergency button. Every response is slow, careful, and filled with uncertainty. Engineers often describe working with Voyager as performing surgery with thick gloves, in the dark, while standing very far away. They rely entirely on data Voyager sends back, data that is increasingly faint and sometimes corrupted by noise. They must guess what is happening on board, then send commands based on those guesses, hoping the spacecraft is still capable of carrying them out. Voyager's inability to think or heal also affects how its end will unfold. There will be no moment where Voyager realizes it is failing. There will be no final attempt to save power or preserve communication. Systems will drop offline one by one as power fades and temperatures fall. Voyager will not adapt to these losses. It will simply keep executing its last instructions, even if those instructions no longer make sense. This rigid behavior is already visible. Some instruments are running at power levels far below their original design limits. Some heaters have been turned off, allowing parts of the spacecraft to drop to extreme cold. Voyager does not complain. It does not signal distress. It continues working until something physically stops it. The lack of self-repair and intelligence is not a weakness in the way it might seem. It is part of what allowed Voyager to last this long. Simpler systems break in simpler ways. Predictable behavior allows engineers to plan far ahead. But it also means that once the decline reaches a certain point, there is nothing left to slow it down. Voyager cannot make sacrifices. It cannot decide to shut down an instrument to save communication. It cannot choose to stop rotating to reduce stress. Every sacrifice must be chosen on Earth and transmitted across billions of kilometers of space. And when the power drops too low, Voyager will not ask what to keep alive. It will simply fail. This is the core truth about Voyager. It is not a survivor. It is not resilient in the human sense. It is a machine following orders until the laws of physics remove its ability to do so. Its long life is not the result of intelligence or adaptation. It is the result of careful design, cautious operation, and a slow, predictable decay. The power that was always running out. Voyager is alive today for one reason and one reason only. Not because it is strong, not because it is smart, and not because it can adapt, but because it carries its own source of heat into the dark. Far from the sun, far beyond the reach of solar panels, Voyager survives on a quiet process that cannot be stopped, slowed, or controlled. The slow decay of a radioactive metal is the only thing standing between Voyager and silence. From the start, engineers knew sunlight would fail them. Past Jupiter, the sun becomes weak, a distant glare that cannot power a spacecraft meant to run instruments, computers, heaters, and a radio strong enough to speak across billions of kilometers. Solar panels would have grown useless quickly, turning Voyager into a dead object long before it reached Saturn. So a different solution was chosen, one that sounds simple but carries consequences that stretch across decades. Voyager was powered by radioisotope thermoelectric generators, devices that do not produce energy by spinning or burning fuel. They work by sitting still and getting hot. Inside each generator is plutonium-238, a material that naturally breaks apart over time. As it does, it releases heat. That heat never stops. It does not need oxygen. It does not need light. It does not need motion. As long as the plutonium exists, it gives off warmth. Voyager carries 3 of these generators, mounted on a long arm away from the main body of the spacecraft. This distance is not for balance or shape. It is to protect Voyager's instruments from radiation. Even so, radiation leaks through, and over decades it slowly damages electronics. The generators are both Voyager's life source and one of its long-term dangers, a trade that was accepted because there was no other way. At launch, the heat from the plutonium was intense. Thermocouples inside the generators converted that heat into electricity, giving Voyager enough power to run everything at once. Instruments, heaters, radios, computers, all of it running together without concern. In those early years, power was not scarce. Engineers did not have to choose between systems. They did not have to make sacrifices. But the decay never pauses. Every year, the plutonium produces a little less heat. Every year, Voyager has a little less power to work with. This was always known. The decline was calculated before launch. What could not be known was how long Voyager's systems would continue working as power dropped lower and lower. Electricity on Voyager is not just about turning things on. It is about heat. In deep space, cold is not just uncomfortable. Cold is fatal. Wires become brittle, fuel thickens, valves stick, sensors drift. Voyager depends on heat to keep itself functioning, and much of that heat comes from the same generators that produce electricity. As power falls, engineers must decide where it goes. Do they keep an instrument alive, or do they keep a heater running? Do they preserve science, or do they preserve the ability to point the antenna at Earth? Voyager does not make these choices. People on Earth do, knowing that every decision shortens the life of something else on board. Over the years, Voyager's power budget has become tighter and tighter. Instruments that once seemed essential were turned off forever. Heaters were shut down, allowing parts of the spacecraft to fall far below their original temperature limits. Systems were pushed into ranges never tested before launch. Each time, Voyager continued working, quietly disproving assumptions about how fragile it was supposed to be. But the power loss is not negotiable. It does not slow down because engineers are clever. It does not care how valuable the data is. The plutonium decays at its own pace, and that pace cannot be changed. Every watt lost is gone forever. Voyager's radio transmitter is one of the most demanding systems on board. Sending a signal across interstellar space requires steady power and stable voltage. As power drops, maintaining a clean signal becomes harder. Noise creeps in, the signal weakens. Earth's massive antennas strain to hear it, filtering out background noise, pulling data from whispers riding on radio waves that have traveled for nearly a full day. The power system also feeds Voyager's attitude control, the system that keeps the antenna pointed at Earth. This requires small bursts from thrusters and constant monitoring from sensors. If power drops too low, Voyager may still be alive, still warm, still full of functioning electronics, but unable to aim its voice in the right direction. In that case, Voyager would effectively be dead to Earth, even though it continues drifting through space. This is one of the cruel realities of Voyager's design. Power does not fail evenly. One system may still have enough electricity, while another does not. Voyager could lose communication before it loses consciousness, not because it shuts down, but because it can no longer speak in a direction anyone is listening. The generators themselves will continue producing heat long after Voyager stops responding. Even when the electricity is no longer enough to run a radio or a computer, the plutonium will keep decaying. The spacecraft will remain slightly warm compared to the surrounding space, a quiet ember drifting through the dark. There is no moment when the generators suddenly stop. There is no dramatic drop. The decline is smooth, slow, and unavoidable. Engineers track it year by year, watt by watt, planning shutdowns months in advance. They know roughly when Voyager will cross critical thresholds. They do not know exactly which system will fail first when those thresholds are crossed. What makes this tense is how close Voyager is now to the edge. The margin between enough power and not enough power is thin. A single unexpected problem, a heater drawing slightly more energy than expected, a voltage fluctuation, a bit of radiation damage that forces a system to work harder, could push Voyager past a point it cannot recover from. Engineers have already taken extraordinary steps to stretch Voyager's life. They have rerouted power in ways never planned. They have accepted colder temperatures than anyone thought safe. They have shut down instruments not because they failed, but because keeping them alive would kill something more important. Voyager, meanwhile, does nothing different. It does not resist. It does not adapt. It simply runs on whatever power it is given, executing commands exactly as instructed. When power is cut to a system, Voyager does not notice the loss. It moves on to the next instruction. The generators also shape how Voyager's end will feel from Earth. There will be no final alert saying power is critically low. There will be no message announcing shutdown. Instead, the signal will grow weaker. Data packets will become harder to decode. Engineers will notice more errors, more retries, more silence between successful transmissions. Eventually, one command will go unanswered, then another. Engineers will wait, listening through the deep space network, hoping Voyager is still there, hoping the antenna is still aligned, hoping the radio still has enough power to whisper back. And at some point, nothing will return. That silence will not mean the generators have stopped. It will mean Voyager no longer has enough power to speak. The spacecraft will continue drifting, warmed by a decaying metal heart, carrying instruments that once rewrote textbooks, carrying a record of Earth meant for no one in particular, moving farther into space with every second. The power that sustained Voyager was never infinite. It was never renewable. It was always running out from the moment the spacecraft left Earth. Everything Voyager has done since then, every image, every measurement, every signal received on Earth has been borrowed time. And that borrowed time is paid back slowly, watt by watt, year by year, as the quiet heat inside Voyager fades, leaving behind a machine that once spoke across the solar system, now moving forward in complete silence, still warm, still intact, but forever beyond reach. Voyager in interstellar space. Voyager is no longer just a spacecraft moving past planets. It has become something far rarer, something that exists in a place no other human-made object has reached. Out there, beyond the Sun's influence, Voyager is traveling through the first layer of space that is truly beyond our solar system. This region is not empty, not calm, not static. It is a storm of particles, magnetic waves, and invisible energy. And Voyager is the only machine we have that can touch it directly, measure it, and tell us what it is like. No telescope on Earth, no satellite orbiting a planet, no space probe near Jupiter could ever give us the same information. Observations from afar can only guess at what is happening at the boundary where the Sun's influence fades. Only Voyager is there, feeling the plasma, counting the cosmic rays, measuring the magnetic fields as they shift and ripple. Every second of data that arrives from the spacecraft is a revelation about the space that surrounds our solar system, a region that until Voyager passed through it was completely unknown. The plasma Voyager measures is one of the most important discoveries. Space may look empty, but it is full of charged particles, and in this distant region, their density, flow, and temperature can reveal how our Sun interacts with the galaxy. Voyager's instruments detect subtle vibrations in the plasma, tiny oscillations that let scientists calculate density even when the particles themselves are invisible. These measurements are unique. No other spacecraft can tell us how thick or thin the plasma is, how it moves, or how it carries energy across this boundary. Voyager also measures cosmic rays, high-energy particles that come from outside our solar system. These rays constantly bombard the spacecraft, invisible but powerful, carrying information about distant supernovae and the galactic environment around us. Voyager counts them, records their energy, and tracks their arrival over time. The data helps scientists understand not just our own neighborhood, but the cosmic forces that shape galaxies far beyond. Each particle Voyager detects is a messenger from the Milky Way itself, and the spacecraft has been catching them continuously for decades. Magnetic fields, invisible lines of force that govern the movement of plasma and charged particles, are another treasure Voyager provides. Instruments on both spacecraft measure the strength and direction of the magnetic field as Voyager moves through interstellar space. These readings show how the Sun's magnetic influence fades and how it interacts with the galaxy. Sometimes the field twists, sometimes it strengthens, and sometimes it drops unexpectedly. Voyager records all of it, painting a dynamic picture of a space environment that was completely unknown before it arrived. Crossing into interstellar space. In 2012, Voyager 1 reached a point no human-made object had ever crossed. It passed through the heliopause, the invisible boundary where the Sun's influence finally gives way to the galaxy. Inside the heliosphere, the solar wind flows outward, carrying magnetic fields and particles from our star. Beyond it, the environment changes completely. The plasma, the magnetic fields, the cosmic rays, all behave differently, and Voyager 1 was the first to feel the shift. The change was sudden, almost shocking. the density of particles outside the heliosphere was higher than expected. The magnetic field, which inside the solar system had been dominated by the Sun, began to interact with the fields of interstellar space in ways scientists had only guessed at. The cosmic rays from the galaxy increased sharply, flooding the spacecraft's detectors. Voyager 1 sent all of this data back to Earth, revealing for the first time what it is like beyond the bubble that surrounds our Sun. Voyager 1 did not just confirm theories, it challenged them. The readings suggested that the heliopause was more dynamic than anyone imagined. Instead of a simple smooth boundary, it behaved like a shifting wall, influenced by the solar wind, the motion of the Sun through the galaxy, and the pressure from cosmic rays pushing in from outside. Every measurement brought new questions, and Voyager 1 had no answers of its own. It could only send back numbers, patterns, and signals for scientists on Earth to decipher. 6 years later, Voyager 2 followed a similar path, crossing the heliopause in 2018. Unlike its twin, Voyager 2 encountered slightly different conditions. The density of plasma, the orientation of the magnetic field, and the levels of cosmic rays were not the same. Scientists realized immediately that the heliopause is not a uniform shell surrounding the Sun. It is asymmetric, stretched and twisted by the movement of the Sun through the galaxy, by variations in solar wind strength, and by the galactic environment beyond. This asymmetry was a surprise. Models had assumed the heliosphere was roughly spherical, like a balloon surrounding the solar system. Voyager 2 showed that the reality is more complicated. The shape of the heliopause depends on external pressure, solar activity, and interactions with interstellar magnetic fields. Some regions are closer to the Sun, others stretch far beyond. The heliopause bends, twists and fluctuates, like an invisible shield pushed and pulled by forces both inside and outside our solar system. Both Voyagers continue to send back data that reveal more than just the location of this boundary. They measure how particles flow from the galaxy into the heliosphere, how magnetic fields twist and reconnect, and how cosmic rays change intensity over time. Each reading from Voyager 1 and Voyager 2 paints a picture of a turbulent, dynamic environment that surrounds our solar system. The data helps scientists understand not only where our solar system ends, but also how it interacts with the galaxy itself. These crossings also highlighted the value of having two spacecraft. Voyager 1 and Voyager 2 took slightly different paths at slightly different angles, and they encountered conditions that were not identical. By comparing their readings, scientists could see that interstellar space is not uniform. It has currents, waves, and regions of higher and lower density. The asymmetry discovered by Voyager 2 revealed that our solar system is moving through a galaxy that is itself dynamic, and that the Sun's protective bubble is flexible and responsive to forces we can only begin to understand. Even today, these readings continue to arrive on Earth, traveling across billions of kilometers, arriving as tiny bursts of radio waves that are almost impossibly faint. They are proof that Voyager is still not just a relic of a mission to Jupiter and Saturn, but an active explorer of the space between stars. The plasma densities, the magnetic field measurements, the cosmic ray intensities all come from a spacecraft launched more than 4 decades ago, now far beyond the planets it was built to study. Voyager 1 and Voyager 2 have turned the heliopause from an abstract boundary on a chart into a real, measurable, living region of space. They have shown that the edge of our solar system is not a calm line drawn in textbooks, but a turbulent frontier shaped by the Sun, by the galaxy, and by the constant flow of particles and energy between them. Each second of data is a reminder that these spacecraft are the only instruments humanity has in this region. No telescope, no orbiting probe, no future mission has yet touched this frontier in the same way. The readings from Voyager 1 and Voyager 2 continue to refine our understanding of interstellar space with every passing day. Scientists track subtle variations in the plasma, watch how cosmic rays change with solar cycles, and monitor shifts in the magnetic field. They compare readings between the two spacecraft, seeing how different paths through the heliopause produce different results. This is a science that could not exist without the Voyagers, because nothing else is there to record it. The key discovery that changed everything. Out there, beyond the planets, beyond the influence of the sun, the space between stars was once thought to be almost empty. Scientists imagined a vast, quiet void, a place where particles were sparse, magnetic fields were weak, and energy flowed gently. They pictured interstellar space as a calm backdrop, a silent stage on which the sun's sphere of influence, the heliosphere, might fade into nothingness. But Voyager told a story no one expected. And that story changed everything we thought we knew about the sun, the galaxy, and our place among the stars. Voyager had been moving outward for decades, carrying instruments designed to measure particles, magnetic fields, and radiation. Its original mission had been simple in comparison to what it would eventually accomplish: visit Jupiter, then Saturn, and, if lucky, Uranus and Neptune. Beyond that, Voyager was never intended to be a deep space explorer. It was not designed to leave the solar system or to survive in the harsh environment beyond the planets. And yet, as it drifted past the known worlds, something remarkable began to appear in its data. For years, Voyager measured the solar wind, the stream of charged particles flowing outward from the sun. This wind creates the heliosphere, a bubble of influence that protects the solar system from the galaxy's harsh radiation. Scientists believed that once Voyager reached the edge of this bubble, the density of particles would drop sharply. Beyond the heliosphere, they expected a thin, sparse plasma, the near-perfect emptiness of interstellar space. They expected silence. They expected calm. Instead, Voyager detected something completely unexpected. The spacecraft measured plasma densities far higher than anything predicted. The interstellar plasma was thicker, more energetic, and more complex than anyone imagined. Voyager's instruments were registering oscillations in the plasma, tiny waves in the charged particles, that revealed a medium full of motion, energy, and structure. Interstellar space was not empty. It was alive, in a way scientists had never experienced directly. This measurement stunned the scientific community. The sun's influence, which extends in the form of solar wind and magnetic fields, was interacting with this dense plasma in ways that had never been anticipated. Voyager showed that the heliosphere extends much farther than any model had predicted. The boundary between solar influence and the galaxy's vast expanse was not a simple line. It was a turbulent, dynamic frontier shaped by the constant push and pull between the sun and interstellar space. The discovery came slowly, almost quietly. Voyager's instruments were designed to measure particle counts, plasma density, and magnetic fields, but the signals arriving from billions of kilometers away were faint, often buried in noise. Engineers and scientists had to sift through mountains of data, look for patterns, and separate what was real from what was interference. Week after week, month after month, they watched as the numbers changed, slowly revealing the unexpected reality. It was Voyager 1 that first confirmed the discovery in 2012. As it crossed the heliopause, the point where the solar wind's influence ends, the plasma readings jumped. The density increased dramatically, much higher than predicted. The magnetic field shifted, and the instruments recorded a sudden rise in galactic cosmic rays, the particles originating outside the solar system. These changes were clear signals that Voyager was no longer inside the sun's bubble. It had entered true interstellar space, a region of dense plasma and energetic particles that no spacecraft had ever measured directly. This was more than just a scientific curiosity. It fundamentally changed how we understand the sun and the solar system. The heliosphere had been assumed to shield the planets and protect them from most interstellar radiation. But Voyager's data showed that this shield extends far beyond what had been predicted. The sun's influence reaches across a vast territory, interacting with the galaxy in ways we can now measure. What seemed like empty space is in fact full of matter and energy, an environment shaped by both the sun and the interstellar medium. The discovery also proved that interstellar space is far from empty. Even at the distance Voyager traveled, billions of kilometers from the sun, Space is filled with charged particles, electromagnetic waves, and magnetic fields. This was something that could only be known by being there. Telescopes, satellites, and Earth-based observations cannot reach this region directly. Voyager is the only machine humanity has that has touched this territory and returned measurements from it. Without Voyager, we might still imagine interstellar space as a near-perfect vacuum, empty and silent. Voyager 2 later confirmed these findings in 2018, crossing the heliopause along a slightly different path. Its plasma measurements matched Voyager 1's observations, but revealed subtle differences in density, magnetic field orientation, and particle flow. The heliosphere is not symmetrical. Its boundaries are stretched, twisted, and shaped by the motion of the Sun through the galaxy. The asymmetry highlights how dynamic and complex the interface between our solar system and interstellar space really is. Voyager's data made clear that we cannot model this region with simple assumptions. It is alive, turbulent, and constantly changing. This discovery is why NASA continues to keep Voyager alive at all costs. The spacecraft may be nearly 50 years old, with failing instruments and a slowly dying power source, but it carries knowledge that cannot be replaced. No mission is currently planned to replicate Voyager's journey, and nothing else has the instruments or trajectory to measure plasma densities, magnetic fields, and cosmic rays in this same region. Voyager is a unique tool, a time capsule of human exploration, and the only way to observe the first direct layer of interstellar space. Every watt of power matters. Every instrument that still works is precious. Engineers carefully manage Voyager's limited electricity, shutting down non-essential systems to preserve the ones that measure plasma and cosmic rays. The Deep Space Network listens day and night, picking up the faint signals that carry this data across billions of kilometers. A single failure could end humanity's direct view of interstellar space forever. The spacecraft's survival is no longer about visiting planets. It is about keeping the first window into the galaxy open as long as possible. The importance of the plasma density measurements cannot be overstated. Before Voyager, models of the heliosphere were largely theoretical. Scientists could simulate the solar wind and cosmic radiation in computers, but the simulations relied on assumptions that could not be tested. Voyager gave those models reality. The plasma readings showed that our understanding of the Sun's influence had underestimated its reach, and that interstellar space is structured, dynamic, and full of energy. Every particle count from Voyager helps scientists refine models of the heliosphere, cosmic ray shielding, and even how stars interact with the galaxy. The discovery also has implications far beyond physics. Knowing the structure and density of interstellar space is crucial for future spacecraft. If humanity ever sends probes beyond the heliosphere, understanding the plasma environment, cosmic ray levels, and magnetic fields will determine how spacecraft are designed and how instruments are protected. Voyager's measurements provide the only real data we have to plan for deep interstellar travel. Even today, as Voyager drifts farther from the Sun, its instruments continue to return plasma readings. Scientists track fluctuations, density waves, and particle flows. They see how cosmic rays change over time and how the magnetic field interacts with the interstellar medium. The spacecraft's observations are like listening to a conversation between the Sun and the galaxy, a dialogue that was once entirely invisible to us. This discovery also reshaped NASA's mission priorities. The agency has invested enormous effort to keep Voyager operational despite its age. Engineers have reprogrammed its computers, rerouted power through decades-old circuits, and accepted temperature and radiation extremes that were never meant to be endured. All of this is done to preserve the instruments that measure plasma density. Without those instruments, we would lose the only direct access humanity has to interstellar space. Voyager's findings have inspired new science and new missions. They feed research into cosmic ray physics, interstellar magnetic fields, and the boundary regions of other star systems. By showing that interstellar space is not empty and that the Sun's influence extends farther than expected, Voyager has created an entirely new field of study. Scientists can now test theories of galactic interaction, study how cosmic particles propagate, and model how other stars' heliospheres might behave. None of this would be possible without Voyager's direct measurements. The key discovery, the higher than expected plasma density beyond the heliosphere, is not just a number on a chart. It is a revelation that transformed our understanding of the solar system's reach. It is proof that space, even where we thought it was empty, is full of structure, energy, and motion. It is the reason Voyager is still alive today, why every effort is made to preserve it, why engineers risk working with circuits decades beyond their expected life, and why the Deep Space Network continues to track its signal with extraordinary patience. Voyager's plasma readings have become the foundation of modern interstellar science. They are a direct measurement, a touchpoint in a place no human can reach. They confirm that our sun's influence is vast, that interstellar space is structured, and that the frontier beyond the heliosphere is a living, changing environment. Scientists rely on this data to test every model, to refine every prediction, and to plan every potential mission that might one day follow Voyager into the galaxy. Even after nearly 50 years, Voyager continues to teach us. Its key discovery, the dense, energetic plasma beyond the heliopause, is a daily reminder that the universe is stranger, more dynamic, and more alive than we ever imagined. Without Voyager, we would be blind to this first layer of interstellar space. With it, we have a voice in the void, a messenger returning with truths about the galaxy that no one else has ever heard. Voyager's journey is far from over. Its power slowly declines, its instruments age, and its systems degrade. Yet every particle it measures, every fluctuation it records, every signal it sends is a testament to a discovery that changed everything. Humanity has only one window into interstellar space, and it is still open because Voyager continues to drift onward, carrying instruments that measure the plasma, cosmic rays, and magnetic fields that define the boundary of our solar system. The key discovery, the unexpectedly high plasma density, is why Voyager matters. It is why NASA keeps it alive at all costs. It is why scientists stare at the faint, delayed signals that arrive every day, decoding the whispers from a spacecraft traveling farther than anything else ever built. Voyager revealed that interstellar space is not empty, that the sun's influence stretches farther than we imagined, and that the universe beyond the heliosphere is alive with energy, particles, and magnetic currents. Voyager's power source explained. Out in the darkness beyond the planets, where sunlight is too weak to reach, Voyager keeps moving, keeps sending signals, keeps exploring, and it does all of this because of a quiet, unassuming source of energy tucked inside its body. It is not a battery you can plug in. It is not a solar panel stretching toward the sun. It is something far older, far stranger, and far more reliable: plutonium-238. Voyager carries a type of generator called an RTG, short for radioisotope thermoelectric generator. The principle is simple but powerful. The plutonium inside naturally breaks apart over time, a process called radioactive decay. As it decays, it releases heat. That heat is not wasted. Inside the RTG, thermocouples convert that warmth into electricity, providing Voyager with the energy it needs to run its instruments, computers, heaters, and its radio that speaks across billions of kilometers of space. There are no moving parts in an RTG. Nothing spins, nothing vibrates, nothing needs maintenance. It does not wear out in the way mechanical engines do. The heat flows constantly, steadily, like a heartbeat that refuses to stop. That is why Voyager can still work today, more than 40 years after it was launched, in a place where the sun's light is too faint to power anything. But even this quiet, constant power is not infinite. Plutonium-238 has a half-life of 87.7 years, which means that over that span of time, half of it decays into other elements. As the plutonium decays, the amount of heat it produces slowly decreases. That decrease translates into electricity. Right now, Voyager loses roughly 4 watts of power every year. It is a tiny number, but in a spacecraft designed to operate with extreme efficiency, every watt matters. Every year, engineers have to make decisions about where that power goes. Some instruments are more essential than others. Some heaters must stay on to prevent delicate circuits from freezing. Some science instruments must be turned off so that the radio can keep speaking to Earth. Voyager does not make these decisions. It cannot. The spacecraft obeys commands sent from engineers on Earth, stretching its dwindling energy in the most efficient ways possible. The RTGs are marvels of engineering. They are small, compact, and capable of operating for decades in the cold vacuum of space. The heat from the plutonium is relentless, flowing through the thermocouples, generating electricity even when the spacecraft is thousands of times farther from the Sun than Earth. It is quiet, invisible, and unglamorous, but without it, Voyager would have gone dark long ago. This generator, powered by decaying plutonium, is why Voyager has outlasted every expectation. It is why instruments continue sending back data, why the radio still whispers to Earth, and why engineers continue to manipulate circuits, reroute power, and keep the spacecraft alive. The RTG does not care about distance, obstacles, or dust in space. It simply produces heat and electricity, slowly diminishing over time, patiently powering a spacecraft far beyond the reach of sunlight. Each year, 4 watts are lost, but each year, engineers make careful choices to stretch that power, keeping the most important instruments alive as long as possible. Voyager's power then and now. When Voyager left Earth in 1977, it carried a total of roughly 470 watts of electrical power, enough to run every instrument, every heater, every computer, and its radio at full strength. For a spacecraft designed to travel billions of kilometers, that might sound small, but engineers had built every circuit, every system, and every instrument to run efficiently within that strict limit. Every wire, every chip, every tiny heater was carefully calculated. There was no margin for waste. Back then, Voyager was like a young runner, full of energy, able to sprint, leap, and record everything in its path. It could take pictures of Jupiter and Saturn at full resolution, measure magnetic fields with precision, count particles flowing from the Sun, and transmit vast amounts of data back to Earth. The spacecraft did all of this without breaking a sweat, drawing on every bit of the 470 watts its RTGs provided. But time is not kind to even the most carefully designed machines. Voyager's power source, its 3 RTGs fueled by plutonium-238, begins a slow, inevitable decline from the moment it is activated. Plutonium decays, heat diminishes, and electricity falls. There is no way to stop it, no way to recharge, no way to replace the fuel. Every year, Voyager loses roughly 4 watts of power. It seems small, almost negligible, but in a spacecraft built with a finite energy budget, every single watt counts. By the mid-2020s, Voyager's available power has fallen to around 250 watts. That is barely more than half of what it had at launch. It is enough to keep some instruments alive, enough to keep the radio speaking across billions of kilometers, enough to maintain critical heaters, but not enough to run everything at once. Voyager cannot record high-resolution images. It cannot operate all of its scientific instruments simultaneously. It cannot maintain the spacecraft in the same state it had when it was exploring Jupiter and Saturn. Every watt has to be carefully assigned, rationed like a scarce resource. Heaters take top priority because cold can be fatal. Without heat, wires become brittle, circuits fail, and instruments can freeze beyond repair. The spacecraft's computers, which control navigation and instrument operation, must remain powered. Without them, Voyager cannot follow commands from Earth. Communication also ranks high. If Voyager cannot point its antenna accurately and transmit signals, all data is lost, even if instruments remain functional. Science instruments are valuable, but not all can be run. Engineers decide which instruments provide the most crucial measurements at any given time. Sometimes a particle detector is kept active while a plasma experiment is turned off. Sometimes magnetic field readings are prioritized over cosmic ray measurements. The choices are carefully balanced to ensure Voyager continues to return the most important information for as long as possible. The contrast between Voyager's original power budget and its current state tells the story of survival. At launch, it could run everything. Today, it survives by careful triage, by turning off some systems, and by stretching the remaining electricity across critical functions. Engineers have rerouted circuits in ways no one imagined, reducing energy loss and extending life. They have accepted extreme cold, pushing instruments beyond the tested range, because the alternative would be silence. Voyager's dwindling power also explains the spacecraft's slow, deliberate pace. It cannot send huge amounts of data at once. It cannot operate multiple instruments continuously. Every signal, every measurement, every packet of information is precious. The spacecraft has become more like a carefully tended flame than a full-powered machine, a flickering light that still carries knowledge across unimaginable distances. The power loss is inevitable, yet it has forced ingenuity. Engineers have adapted. Commands are sequenced to make the most of every watt. Instruments are turned on and off according to precise schedules. Heaters are allowed to drop below ideal temperatures, stretching limited energy to preserve systems that keep Voyager alive. The spacecraft is no longer a youthful explorer running at full strength. It is a veteran survivor, kept alive by careful management, by strategy, and by the slow but steady heartbeat of its RTGs. The story of Voyager's power, from 470 watts at launch to roughly 250 watts today, is the story of survival against impossible odds. It is a story of planning, patience, and precision. Every watt that remains is a victory against time, distance, and decay. Every signal that reaches Earth is a reminder that even in the cold, empty stretches of space, a tiny machine can keep speaking, keep measuring, and keep exploring, powered by the slow, steady warmth of decaying plutonium. Even as the watts continue to decline, the spacecraft presses on. Every year, engineers make decisions that extend its life. Every measurement, every transmission, every pulse of data is precious because once a system goes dark, it cannot be restored. The original 470 watts that once ran every system have been reduced, but the mission continues, proving that even half the power, carefully managed, is enough to keep humanity's most distant explorer alive, still whispering across the dark, still carrying the legacy of exploration further than anyone ever imagined. The engineering reality. Voyager is not dying in an instant. It is not exploding, failing, or shutting off with a dramatic flare. It is dying slowly, quietly, in pieces, subsystem by subsystem. Each system that fails is a reminder that time and distance are absolute. Every watt of power lost carries consequences, and engineers on Earth spend every day calculating what that loss will mean. Heaters are the most critical of these systems. Voyager drifts in a place where the cold is absolute, where space itself is nearly as cold as the sun's shadow. Without heat, delicate parts of the spacecraft are vulnerable. Fuel lines, once fluid and reliable, begin to freeze. The hydrazine used to fire the thrusters thickens and valves grow stiff. Thrusters that were meant to adjust the spacecraft's orientation or fire in precise bursts lose responsiveness. Attitude control, the spacecraft's ability to keep its antenna pointed at Earth, becomes tenuous. A single frozen fuel line can prevent a perfectly functioning radio from transmitting a single signal. Power loss does not mean instant death for Voyager. It does not suddenly fall silent. Instead, systems begin shutting down in sequence, one by one. Instruments are turned off first, sacrificed so that heaters, computers, and the radio can continue to function. The spacecraft grows colder, slower, quieter. Engineers make these choices deliberately, turning off the non-essential, monitoring what can survive, stretching every watt until the limits of the RTGs can no longer be managed. As each subsystem fails, the spacecraft becomes simpler, more vulnerable. Computers that once coordinated complex observations are reduced to basic command processing. Instruments that measured cosmic rays, plasma density, and magnetic fields are sacrificed to preserve communication. Thrusters fail first in minor ways, then major, until the spacecraft can barely orient itself. Heaters fail, and parts of Voyager fall below safe temperature limits, risking permanent damage. Every failure is a domino, tipping the next in line. This slow death is the reality of deep space exploration. Voyager cannot repair itself. It cannot reroute around broken circuits unless engineers explicitly command it to. It cannot produce more power. Every action is carefully managed from Earth, a delicate balance between survival and science. When an instrument is shut off to save a heater, the choice is permanent. The spacecraft does not recover. Even in this state, Voyager continues to operate. Its sensors still record data. Its radio still whispers signals across billions of kilometers. But every signal comes at a cost. Every command sent from Earth must consider the limited power remaining, the weakening thermal environment, and the growing fragility of the spacecraft. The mission has become a careful orchestration of what can survive longest, with every system sacrificed in turn to preserve the most critical: communication, orientation, and minimal thermal control. The engineering reality is harsh. Voyager's decline is measured in watts and degrees, in frozen fuel lines and failed thrusters, in the slow march of time. The spacecraft is alive, but only just. It is a veteran explorer, moving through interstellar space with systems shutting down piece by piece, a reminder that even the most carefully built machine cannot escape the laws of physics. Even as heaters fail and thrusters lose functionality, the spacecraft continues to drift forward. It cannot turn around. It cannot repair damage. It cannot generate new power. It survives on the bare minimum, with Earthbound engineers deciding which functions remain alive and which are sacrificed. Each subsystem lost is a small death, a fading heartbeat in the body of a machine that has already traveled farther than any human being, farther than any other spacecraft, farther than almost anyone could imagine. The shutdown strategy. Voyager cannot live forever. Its power is fading, its systems are wearing down, and the cold of space waits silently for every component to fail. But NASA engineers refuse to let it die haphazardly. They have a plan, a careful, deliberate strategy designed to keep Voyager alive for as long as possible. They call it controlled shutdown, but it is more like a carefully measured euthanasia, executed with precision, patience, and care. The idea is simple in concept, but delicate in execution. Engineers prioritize the spacecraft's most vital function: communication. Everything else, the instruments that measure cosmic rays, plasma, and magnetic fields, the cameras that once captured planets in breathtaking detail, is secondary. Each system that consumes electricity, each instrument that draws heat, becomes a candidate for shutdown. The goal is clear: keep the transmitter alive, keep the antenna pointed at Earth, keep the whispers of Voyager traveling across billions of kilometers. One by one, instruments are turned off. The process is deliberate. Engineers analyze which systems are expendable at any given moment, which ones can be sacrificed without jeopardizing the survival of others. When a detector measuring cosmic rays is turned off, it is not a failure, but a strategic choice. When a plasma experiment goes dark, it is a calculation, not a loss. Each shutdown preserves the essential systems that allow Voyager to keep speaking. The sequence is slow, measured in weeks and months. There is no rush. Turning off an instrument too early risks losing valuable scientific data. Leaving it on too long risks draining the limited power needed for heaters or the radio. Engineers balance every decision against the harsh reality of space. Temperatures that can freeze circuits, thrusters that will eventually fail, and a power source that declines a few watts each year. Every choice is a trade-off. Every decision matters. Heaters are kept online as long as possible because they protect fragile components. Computers are carefully maintained to ensure they can process commands from Earth. The radio is the highest priority, the single link that carries Voyager's voice across the void. Instruments that once made the spacecraft a full-fledged laboratory are sacrificed to protect these essentials. Each shutdown is quiet, invisible, and irreversible. The spacecraft does not know it is losing its sensors. It simply continues, stripped of capabilities, surviving on the bare minimum. This strategy is unique in the history of spaceflight. Engineers have never managed a spacecraft in interstellar space before, never faced the challenge of rationing power so carefully while continuing to gather data. There are no backup systems, no spare instruments, no way to restore lost power. Every watt saved translates into months or even years of extended communication. Every system turned off is a victory against time and distance. The shutdown process also reflects the extreme ingenuity of the engineering team. Circuits are rerouted, instruments are powered down remotely, heaters are selectively turned off and on, and commands are sequenced to maximize the life of critical systems. Engineers monitor telemetry constantly, predicting how each shutdown will affect temperature, orientation, and the ability to send data. Even a single miscalculation could jeopardize months of work, so every decision is made with extreme care. In this way, Voyager survives not because it is indestructible, but because engineers have mastered the art of controlled decline. The spacecraft becomes simpler with each shutdown, reduced to the essentials, yet still alive, still measuring, still speaking. Its voice grows quieter as instruments are sacrificed, but it never goes silent prematurely. NASA stretches its life through careful planning, keeping the link to Earth alive longer than anyone could have imagined. This shutdown strategy is ongoing. Instruments continue to be sacrificed, systems continue to be rerouted, and the balance between science and survival continues to shift. Voyager drifts through interstellar space, slowly losing capabilities, but each decision ensures that the most important functions, the transmitters, the heaters, the computers that keep it pointing correctly, remain operational. The spacecraft has become a managed survivor, a machine whose life is dictated by careful human choices millions of kilometers away. The controlled shutdown is both brutal and beautiful. It is brutal because instruments that once collected groundbreaking data are turned off forever. It is beautiful because it is deliberate, intelligent, and ensures that Voyager continues to deliver the single most precious gift it can: communication from the edge of interstellar space. Engineers manage life and death in a way no human being ever could for a machine drifting where no repair crew can follow, where the cold of space and the decay of time are absolute. Even as power dwindles and systems fade, the shutdown strategy continues to work. Every instrument sacrificed preserves life elsewhere in the spacecraft. Every carefully timed command extends the life of the transmitter, letting Voyager whisper its discoveries across billions of kilometers, letting humanity listen in on the first direct measurements from the space beyond the sun. Engineers make these decisions with precision, care, and an understanding that every choice matters in a machine that has already survived far longer than anyone imagined. Voyager's survival now depends entirely on this strategy. The spacecraft cannot recover lost systems, cannot generate new power, cannot adapt on its own. Its life is a story of careful planning, of measured sacrifice, and of unwavering human attention. Each shutdown is a step closer to silence, yet also a step further into the unknown, keeping alive the faint, valuable connection between a distant explorer and the people on Earth who refuse to let its voice fade. Instruments already turned off. When it launched in 1977, Voyagers had cameras, spectrometers, particle detectors, magnetometers, plasma probes, and multiple other instruments, each designed to capture a piece of the solar system's mysteries. These instruments worked together like a team, gathering data from Jupiter's storms, Saturn's rings, and the distant planets that had never been seen up close. They were Voyager's eyes, ears, and sensors, translating the invisible and the far away into numbers, images, and measurements that humans could study back on Earth. But Voyager is no longer the same spacecraft it once was. Over the decades, the steady decline of power from its RTGs, the cold of deep space, and the careful management by NASA engineers have led to a gradual shutdown of instruments. Some of the most dramatic examples came decades ago, as engineers faced the first hard choices about what to keep alive and what to sacrifice. The cameras, once Voyager's most visible and celebrated tools, were the first to go. In 1990, after nearly 15 years of service, the cameras were turned off permanently. They had already captured humanity's most iconic views of the outer planets, but their operation consumed precious watts that were increasingly scarce. Turning off the cameras was more than a technical decision. It was a symbol of a new era for Voyager. The spacecraft was no longer a planetary explorer. It was becoming an interstellar probe. The images of Jupiter's storms, Saturn's rings, Uranus's faint blue hue, and Neptune's distant dark atmosphere had already changed human understanding forever. Those cameras had done their job, leaving a legacy of beauty and data, but the power required to keep them running could now be redirected towards systems that ensured the spacecraft's survival in the emptiness of space. From that point on, every shutdown became a strategic choice, a carefully measured sacrifice for the greater goal of keeping Voyager alive. The ultraviolet spectrometer was another instrument that fell silent years after the cameras. Designed to study the ultraviolet light from planets and the Sun, it had provided critical data during Voyager's flybys of the outer planets, revealing atmospheric composition, auroras, and particle interactions invisible to the human eye. But by the time the spacecraft was heading toward interstellar space, the UV spectrometer's measurements were no longer essential. Its electrical draw could instead support heaters or the radio transmitter. Engineers made the choice to turn it off, knowing that its legacy had already contributed to decades of scientific understanding. Similarly, the planetary radio astronomy experiment was sacrificed as part of the ongoing struggle to stretch the RTG power. This instrument had measured radio waves emitted by planets, mapping their magnetic environments and detecting auroral phenomena. It had recorded the hidden rhythms of Jupiter and Saturn, the subtle whispers of magnetic storms and charged particles interacting with planetary atmospheres. But in the cold darkness beyond the planets, its readings were no longer mission critical. The power it consumed could instead help keep the spacecraft oriented toward Earth or maintain the warmth of vital systems. With careful planning, the engineers gradually shut down the radio astronomy experiment, each action deliberate, each watt saved, bringing a small extension to Voyager's life. The infrared interferometer, an instrument capable of detecting heat and infrared radiation from planets and their moons, was also turned off in this careful, staged process. During planetary flybys, it had revealed temperature differences, helped map atmospheric layers, and uncovered subtle thermal details invisible to visible light cameras. But in the vast emptiness beyond Neptune, infrared measurements were no longer as urgent. The electricity needed to keep this instrument active was better spent keeping heaters on, keeping the spacecraft's computers functioning, and ensuring that the radio continued transmitting data back to Earth. These shutdowns were not random or reactive. They were planned, deliberate, and carefully executed by teams of engineers and scientists who understood that every watt mattered. Each instrument was analyzed for its importance in the new mission, survival in interstellar space. Every electrical draw was weighed against the value of the data it could produce versus the cost to the spacecraft's remaining life. In this way, Voyager's original suite of instruments was gradually reduced to the minimum required for its interstellar mission, primarily plasma sensors, cosmic ray detectors, magnetometers, and the instruments needed to ensure the spacecraft could continue to point its antenna toward Earth. The process of turning off instruments was a mixture of engineering precision and strategic sacrifice. Engineers had to consider the spacecraft's thermal environment, the remaining fuel for thrusters, the slow decay of plutonium in the RTGs, and the need to maintain orientation control. If a heater went offline, a circuit could freeze. If an instrument drew too much power, the transmitter might lose strength. Every shutdown required calculations, simulations, and a deep understanding of how one system's loss could ripple across the spacecraft. It was a process that combined decades of experience, deep technical knowledge, and the willingness to accept that some data would no longer be collected. Turning off the cameras, UV spectrometer, radio astronomy experiment, and infrared interferometer marked the beginning of Voyager's transformation from planetary explorer to interstellar sentinel. These instruments had defined the spacecraft's early mission, providing humanity with its first close-up look at the outer planets. Their shutdowns signaled a shift in focus. Survival and communication had become paramount. In a way, each instrument turned off was a small death, a silent reminder that even the most advanced machines cannot escape the passage of time and the limits of physics. The shutdown of these instruments also changed the way scientists interacted with Voyager. No longer could they command it to take spectacular images or perform complex experiments. Instead, the focus shifted to interpreting data from the remaining instruments, reading plasma densities, cosmic ray intensities, and magnetic field measurements. These measurements, while less visually spectacular, were more critical for understanding the boundary of the solar system and the nature of interstellar space. Voyager's mission had evolved, and the spacecraft itself had become an instrument of survival as much as science. Even now, decades after these shutdowns, the impact of these early sacrifices is clear. Voyager's RTGs continue to lose power, the spacecraft drifts farther from the Sun, and every system is still carefully managed. By turning off instruments that had already completed their mission, engineers preserved the spacecraft's ability to communicate and collect the most essential data. Without these early shutdowns, Voyager would have long since lost the power needed to transmit its remaining readings back to Earth. The story of the instruments already turned off also underscores the fragility of space exploration. Each system was designed to function perfectly, but space is harsh and unyielding. Electrical power is limited, temperatures are extreme, and repairs are impossible. Engineers must anticipate every eventuality, from freezing fuel lines to failing thrusters, and decide which systems can be sacrificed to preserve life. The cameras, spectrometers, and radio instruments had already given humanity immense knowledge, and their shutdowns were an acknowledgement that, in the battle against time and decay, survival must take precedence over data collection. The gradual loss of these instruments also reveals a human element in Voyager's mission. Engineers and scientists, watching billions of kilometers from Earth, had to make decisions that were permanent, irreversible, and impactful. They had to weigh the value of historical scientific data against the survival of a spacecraft in interstellar space. Each command to turn off an instrument was a conscious choice to preserve life over capability, to trade short-term gain for long-term survival, and to ensure that Voyager could continue to be humanity's only eyes and ears in the space beyond the Sun. Even as the cameras, UV spectrometer, radio astronomy experiment, and infrared interferometer were sacrificed, Voyager continued to provide unprecedented insights. The remaining instruments became the spacecraft's lifeline, feeding data about plasma, cosmic rays, and magnetic fields across the void. The shutdowns allowed the spacecraft to conserve energy for the systems that matter most, ensuring that even as it ages and its power wanes, Voyager can still fulfill its new role, the first and only human-made object to explore interstellar space directly. These early shutdowns were a rehearsal for the strategy that continues today. Engineers now face even more critical choices as power declines further and heaters, computers, and orientation systems compete for dwindling electricity. The principle remains the same: sacrifice what is expendable to keep the spacecraft alive as long as possible. But the stakes are higher, the systems more fragile, and every watt of power more precious than ever. Voyager's story is a story of evolution, adaptation, and survival. The instruments already turned off mark the transition from a fully capable planetary explorer to a minimalist interstellar probe. They show the careful, deliberate planning required to extend the life of a spacecraft far beyond its original mission. They demonstrate the patience and ingenuity of engineers who manage life and death from billions of kilometers away, making permanent choices that affect the only human-made object to explore the space between the stars. And even as the spacecraft drifts farther into interstellar space, its instruments gone one by one, Voyager continues to transmit, continues to survive, and continues to prove the value of these early sacrifices. Each shutdown was a small, deliberate act that preserved the spacecraft's most vital functions, and each decision echoes across decades, allowing humanity to listen to a voice from a place no one else has ever reached. Among the instruments that remain operational on Voyager, the Cosmic Ray Subsystem, or CRS, is the most resilient. Its primary function is to measure high-energy particles coming from the Sun and from beyond the solar system. These cosmic rays carry information about the environment of interstellar space, the density of charged particles, and the structure of magnetic fields that Voyager passes through. CRS is designed to detect these particles with high precision, allowing scientists to track fluctuations and gain insight into the conditions far beyond the planets. The CRS is extremely low power, consuming only a fraction of the energy required by older instruments like cameras or spectrometers. This low power draw makes it one of the most enduring instruments on Voyager. Its electronics are simple and robust, built to operate in the cold, harsh environment of space for decades. Its sensors are shielded and carefully designed to avoid degradation from the very cosmic rays it measures. Because of these factors, engineers expect CRS to remain operational longer than almost any other instrument aboard either spacecraft. However, CRS is not immune to failure. The most likely failure modes involve radiation damage and gradual degradation of electronic components. Even the simplest circuits slowly change over decades in deep space due to cumulative exposure to high-energy particles. Thermally, the instrument relies on the spacecraft's heaters to maintain operational temperatures. If heaters fail, CRS components could freeze, reducing sensitivity or shutting down entirely. Power reductions from declining RTG output can also limit the instrument's ability to record data at full precision, forcing engineers to throttle its activity or lower its sampling rates. Plasma Wave Subsystem, PWS, and Magnetometer, MAG. The Plasma Wave Subsystem, or PWS, is one of Voyager's most important remaining instruments for exploring interstellar space. Its role is precise. It detects oscillations in the density of charged particles, known as plasma, that pervade the space beyond the Sun's influence. When Voyager crosses into interstellar space, the plasma there is far thinner than in the solar wind, yet it still carries waves that PWS can detect. These oscillations are the only direct way to measure the density and motion of interstellar plasma. Unlike other instruments that indirectly infer conditions, PWS senses the very vibrations of particles in the medium Voyager travels through, providing a literal heartbeat of the space environment. PWS is extremely sensitive to temperature. Its electronics and sensors are calibrated to function within a narrow thermal range. If the spacecraft's heaters fail, or if temperatures drop too low, the sensors can freeze or behave unpredictably, producing false readings or stopping altogether. The antennas used by PWS are delicate. They extend from the spacecraft to pick up weak oscillations in plasma. Thermal contraction in the extreme cold of interstellar space can alter the geometry of these antennas, reducing their sensitivity. Power fluctuations also directly affect the instrument's operation. Even minor drops in available electricity can reduce the instrument's sampling rate, lowering the resolution of data. Engineers carefully manage spacecraft power to maintain PWS operation, because once the instrument goes offline, its function cannot be restored. The PWS system works by converting the motions of plasma into measurable electrical signals. These signals are then processed to reveal frequency and amplitude patterns that correspond to the density and movement of charged particles. Because plasma density in interstellar space is extremely low, far lower than near the planets, the instrument must be sensitive to very small signals. Any instability in temperature, voltage, or orientation can overwhelm these small signals with noise, rendering data useless. The combination of extremely low signal strength and sensitivity to the environment makes PWS one of Voyager's most fragile instruments. Yet it remains operational because it draws very little power, and engineers prioritize its heaters and circuits above non-essential systems. The magnetometer, MAG, is another surviving instrument, mounted on long booms to isolate its sensors from the spacecraft's electrical and magnetic interference. MAG measures the direction and strength of magnetic fields, providing crucial information about both the solar wind's outer boundary and the magnetic environment of interstellar space. The booms extend far from the spacecraft body to avoid contamination from Voyager's own electronics, but this design makes the instrument extremely sensitive to movement. Any rotation or drift in the spacecraft's orientation directly affects the accuracy of MAG's readings. If attitude control falters due to failing thrusters, frozen fuel lines, or power loss, the instrument cannot maintain a fixed position, and measurements degrade or fail entirely. MAG's electronics are relatively robust, but the instrument relies on stable temperature and power to maintain calibration. Extreme cold can alter sensor behavior, while voltage drops can reduce measurement resolution. Because the magnetometer is mounted far from the spacecraft, it is also physically vulnerable. If structural components shrink or contract in the cold, or if the booms are jolted by thruster anomalies, the sensors could misalign. MAG is effectively tethered to the spacecraft's overall health. It dies when attitude control weakens, meaning its survival depends on both power for orientation systems and thermal regulation. Both PWS and MAG illustrate the delicate balance Voyager must maintain in interstellar space. PWS is vulnerable to heater shutdowns, while MAG is vulnerable to orientation failure. Their operation relies on a combination of minimal power, precise thermal control, and functioning spacecraft subsystems. Each is highly sensitive to the environment, yet both remain among the few instruments still returning unique scientific data decades after launch. Their survival is a product of careful engineering, power management, and constant monitoring from Earth. The interplay of vulnerability and endurance is clear in these two instruments. PWS requires stable temperature to detect minute plasma oscillations. MAG requires stable orientation to measure fields accurately. Any failure in the spacecraft's heaters, thrusters, or power systems directly threatens these measurements. Engineers manage these risks through careful prioritization of power, adjusting heater usage, and planning spacecraft orientation maneuvers to minimize stress on the instruments. Unlike older high-power instruments that have been shut down permanently, PWS and MAG continue to provide critical insights because their design, power requirements, and placement allow them to survive within the spacecraft's shrinking energy budget. The PWS system functions by detecting the electric field oscillations generated by plasma particles. These oscillations are measured as voltage variations across its antennas. The data is then digitized and transmitted back to Earth, where scientists analyze the frequency and amplitude to determine plasma density and variations in interstellar space. Even small errors caused by temperature instability or power fluctuations can alter these readings. If the spacecraft cools too much, the analog to digital conversion circuits may drift, producing inaccurate measurements. MAG, on the other hand, uses fluxgate sensors mounted at the ends of the booms to measure the three-dimensional magnetic field vector. Its readings depend on both the instrument's orientation and the spacecraft's ability to maintain a steady attitude. Any rotation introduces noise and uncertainty. The booms themselves must remain structurally sound. Thermal contraction or vibrations can misalign the sensors. The instrument is highly dependent on power for calibration and signal processing, so any drop in available energy reduces its accuracy. In terms of failure sequence, PWS is more likely to stop first if heaters fail, because thermal instability directly affects its electronics and antennas. MAG, in contrast, may continue providing measurements as long as orientation is stable, but once attitude control weakens, its readings become unreliable and ultimately useless. Both instruments are extremely sensitive, yet their low power requirements and careful prioritization make them the last remaining windows into interstellar space. Critical discovery from instrument shutdowns. When engineers began turning off Voyager's instruments one by one, they expected the spacecraft to struggle. The power budget was shrinking, the heaters were running on the edge, and every system was being pushed to survive on less than it had ever been designed for. The original design assumed that below certain power thresholds, the spacecraft would fail, instruments would die, heaters would freeze, and communication could be lost. Every calculation predicted that once the power dropped past a minimum level, Voyager would no longer function. But what actually happened surprised everyone. As each instrument was shut down, cameras first, spectrometers next, then radio experiments, Voyager kept operating. Systems that were supposed to fail immediately continued to function. The spacecraft's heaters, thrusters, computers, and communication systems survived on far less power than engineers had thought possible. Instruments like the plasma wave subsystem and the cosmic ray subsystem continued collecting data even as power fell below previously established minimums. Voyager had defied expectations. This unexpected resilience led to a breakthrough in understanding spacecraft survival. Engineers realized that Voyager could handle a much lower energy input than its specifications suggested. The spacecraft was able to prioritize critical functions automatically, reroute power, and maintain life-supporting systems, even as non-essential instruments were turned off. Every shutdown taught the team something new: how to stretch power further, which systems could survive cold conditions, and how to sequence shutdowns to maximize operational life. Each lesson became a new rule for keeping Voyager alive. Because of this discovery, NASA changed the way it managed the spacecraft. They no longer assumed strict power limits would immediately disable Voyager. Instead, engineers began testing how far the spacecraft could go, carefully experimenting with heater schedules, instrument shutdown sequences, and power rationing. This knowledge allowed Voyager to operate decades longer than anyone had planned. Instruments that should have stopped functioning in the early 1990s continued returning valuable data. Even now, the spacecraft survives in interstellar space, over 40 years after launch, because engineers learned that it could handle conditions far beyond its original design. This critical discovery also changed the mindset for future missions. Engineers saw that spacecraft could survive under extreme conditions if power management was carefully controlled, if systems were sequenced intelligently, and if non-essential functions were sacrificed first. Voyager became a living experiment in survival, proving that the limits set on paper were not absolute. Its continued operation is a direct result of this understanding, showing that careful shutdowns do not just save power, they rewrite the rules of what a spacecraft can endure. Every time Voyager's systems cycle through these careful shutdowns, the spacecraft proves its resilience again. The lessons learned have allowed it to keep transmitting, to keep measuring cosmic rays, plasma, and magnetic fields, and to continue giving humanity a window into the space between the stars. Engineers continue to apply these lessons, making minute adjustments, stretching power, and prioritizing systems in ways that allow Voyager to survive, even as it moves ever deeper into interstellar space. What space is doing to Voyager right now? Voyager is flying through a place no spacecraft was ever designed to survive for this long. There is no shield. There is no safe zone. There is no pause button. Right now, as you hear this, Voyager is being hit non-stop by radiation from every direction. Not sunlight, not solar wind. This is galactic radiation, the kind that comes from exploding stars, collapsing suns, and violent events that happened millions of years ago. These particles cross entire galaxies, and now they are passing straight through Voyager's body. Galactic cosmic rays are not gentle. They are high-energy particles moving at near light speed. When they strike Voyager, they do not bounce off. They pass through metal, circuit boards, wiring, memory chips, and sensors, as if the spacecraft were almost transparent. Each particle carries enough energy to damage electronics at the smallest level. They flip bits, they corrupt memory. They inject false signals into systems that were never designed to deal with this kind of environment. When Voyager was launched in 1977, engineers expected it to deal mostly with radiation near planets and the Sun. Jupiter alone is a radiation monster, and Voyager survived that. But interstellar space is different. Out here, there is no magnetic shield from the Sun. The heliosphere once acted like a giant bubble, deflecting many of these particles away. Voyager has now crossed beyond that bubble. The shielding is gone. Every cosmic ray that comes this way has a clear shot. Inside Voyager are computers built with 1970s technology. These are not modern processors. They do not have error correction systems like today's machines. They do not expect memory bits to randomly change value. But now, that is exactly what is happening. A single cosmic ray can strike a memory cell and flip a 1 into a 0. That sounds small, but in a spacecraft computer that can change instructions, alter data, or break entire command sequences. Engineers on Earth see this happening in real time. Data arrives corrupted. Numbers are wrong. Telemetry does not make sense. Sometimes, Voyager sends back information that looks impossible, temperatures that should not exist, voltages that do not match reality. At first, these look like system failures. But then patterns emerge. Engineers trace the issue back to memory corruption caused by radiation hits. This is not theoretical. This is not simulated. This is happening right now. As Voyager moves farther into interstellar space, the frequency of these errors increases. The farther it goes, the more exposed it becomes. Radiation damage is cumulative. It does not heal. Every hit slightly degrades the system. Over time, errors happen more often. Commands fail more frequently. Systems behave unpredictably. Voyager's computers were never meant to be updated like modern software. There is no operating system patching in the way we think of today. Everything on board was written decades ago, burned into hardware, carefully timed, carefully structured. And yet, engineers are now doing something extraordinary. They are rewriting parts of Voyager's behavior remotely. They are uploading patches to computers that are nearly half a century old. This is not like updating a phone. Every command takes over 22 hours to reach Voyager, another 22 hours for confirmation to return. If a patch goes wrong, there is no undo button. A single mistake could permanently disable the spacecraft. Engineers must predict how corrupted memory behaves, how flipped bits affect execution, and how to reroute around damaged sections of memory. They do this by studying patterns in Voyager's failures. When data corruption increases in a specific subsystem, engineers isolate the affected memory addresses. They then modify the way the spacecraft uses that memory, avoiding damaged regions, rewriting instructions so they load from safer areas. This is surgery performed across billions of kilometers, with no physical access, on hardware built before personal computers existed. Radiation also affects Voyager's sensors. Some instruments slowly become noisier. Signals become harder to distinguish from background interference. Cosmic rays create false readings, sudden spikes that do not reflect real conditions. Engineers must filter this out on Earth, separating real data from radiation artifacts. As radiation increases, this becomes harder. The spacecraft itself provides almost no protection. Voyager was never meant to be armored. Thick shielding would have added weight and reduced launch capability. Instead, Voyager relies on distance and luck. But luck wears thin over decades. Every year in interstellar space increases the probability of a critical radiation hit, one that affects a key system instead of a non-essential one. The radio system is especially vulnerable. Corrupted memory and communication subsystems can distort signals, alter encoding, or break synchronization with Earth. Engineers constantly monitor Voyager's signal integrity. When corruption appears, they adjust transmission rates, change command formats, and simplify data packets to reduce the chance of errors. Voyager now speaks more slowly, more carefully, using simpler structures, to survive the hostile environment. Radiation does not kill Voyager instantly. It wears it down, slowly, bit by bit, instruction by instruction, system by system. The spacecraft becomes less predictable, more fragile, harder to manage. Engineers are no longer just operating a probe, they are fighting entropy. What makes this remarkable is that Voyager is still functioning at all. Most modern spacecraft would fail quickly under this level of radiation without active protection and advanced error correction. Voyager survives because its systems are simple, because its software is minimal, and because engineers deeply understand every line of code and every behavior pattern. Each new radiation-induced failure forces engineers to adapt. They learn how Voyager behaves when memory is damaged. They learn which systems tolerate errors and which do not. This knowledge feeds back into new strategies, new patches, new ways to keep the spacecraft responsive. Voyager becomes less capable but more specialized, stripped down to the essentials needed to keep transmitting. Radiation also affects timing. Voyager's clocks drift. Instructions execute slightly out of sequence. Small timing errors compound over long periods. Engineers compensate by adjusting command timing, spacing instructions further apart, giving systems more time to respond. This slows operations but increases survival. Nothing about this is automatic. Voyager does not protect itself. It does not know it is being damaged. Everything that keeps it alive is the result of human intervention, constant monitoring, and deep familiarity with a machine launched before most of today's engineers were born. Right now, cosmic rays are passing through Voyager, flipping bits, injecting noise, weakening systems. Engineers on Earth are watching for the next failure, the next corrupted memory block, the next subsystem that behaves strangely. They are ready to respond, to rewrite, to reroute, to simplify, to sacrifice functionality in exchange for survival. Radiation is not an enemy Voyager can escape. It is the environment itself. And the farther Voyager goes, the worse it gets. Thermal extremes. What space is doing to Voyager right now? Out where Voyager is flying, cold is not a temporary condition and not something that comes and goes. It is constant, permanent, and slowly getting worse. The sun no longer provides any meaningful warmth. At this distance, sunlight is just another faint background glow, and the spacecraft is surrounded by interstellar space that sits only a few degrees above absolute zero. Voyager was never designed for this environment. Every assumption built into its design expected heat to always be available in some form, either from the sun or from onboard systems that were never meant to run this long. Inside the spacecraft, temperatures are now falling below limits that engineers once treated as absolute. These were not flexible guidelines. They were hard boundaries that defined whether a component was considered safe to operate at all. Today, some Voyager components are functioning at temperatures as low as -60 degrees Celsius. In the 1970s, engineers would have assumed that electronics exposed to that level of cold would fail quickly and permanently. What is happening instead is something no one predicted. Many of those systems are still working, even as they drift further into conditions they were never tested for. Voyager does not have heaters powered by sunlight. It never did. Nearly all of its internal heat comes from waste energy, the excess warmth produced by its power source and its electronics while they operate. When the spacecraft had plenty of electrical power, this waste heat was enough to keep the internal environment stable. As power declines, that invisible heat source shrinks with it. Less power means fewer systems can stay active, and fewer active systems means less heat circulating inside the spacecraft. Temperature does not drop suddenly. It falls slowly, year after year, as one heater after another is shut down to save power. Cold in space causes problems that do not show up in warm laboratories on Earth. Metals contract as temperatures fall, and they do not all contract at the same rate. Over decades, this gradual shrinking places stress on solder joints, electrical connectors, and wire terminations that were hand-built more than 50 years ago. These joints were never expected to endure half a century of thermal stress in deep space. Tiny cracks can form in solder or connectors, and a crack too small to detect from Earth can still break a circuit forever. Once that happens, there is no repair and no workaround. Lubricants are another quiet problem. Voyager has very few moving parts because engineers avoided them whenever possible. But some systems still rely on lubricated mechanisms, especially those involved in orientation and antenna pointing. These lubricants were designed to stay fluid within a specific temperature range. As the spacecraft grows colder, the lubricants thicken. They do not freeze solid, but they become sticky and resist movement. Motors and actuators must work harder to move, even though they now have less electrical power available than at any time in the mission. If a motor stalls because the lubricant becomes too thick, it may never start again. The internal temperature of Voyager is not uniform. Some parts of the spacecraft are warmer than others, depending on which systems are still powered and which heaters remain active. As more heaters are turned off, temperature differences inside the spacecraft grow larger. One side of a component may be relatively warm, while another side continues to cool. This uneven contraction places additional stress on materials and solder joints. On Earth, engineers work hard to avoid these temperature gradients because they are known to shorten the life of electronics. Voyager no longer has the ability to control them. One of the most dangerous moments for any Voyager subsystem is a shutdown. Many components are still alive today because they have never been turned off. As long as a system stays powered, it generates a small amount of internal heat that helps it survive the cold. If that system shuts down and cools completely, restarting it in extreme cold may be impossible. Engineers are often less afraid of a system running weakly than they are of turning it off and attempting to bring it back online later. A component that fails while warm might recover. A component that goes cold is often lost for good. As temperatures dropped lower than expected, engineers began noticing something unsettling and remarkable at the same time. Systems were continuing to function below their minimum rated temperatures. These were limits that had been treated as firm boundaries during design. Voyager was operating in a zone that engineers never planned for, and yet it was not failing in the ways they expected. This forced mission teams to rethink their assumptions about what the spacecraft could tolerate. If Voyager could survive colder conditions than originally believed, heaters could be shut down earlier than planned, freeing power for critical systems like communication. That realization alone extended the mission by years. Temperature sensors on board Voyager continue to send back data, and their readings tell a simple story. Internal temperatures keep falling. There is no stabilization point and no new balance waiting to be reached. Every year, thermal margins shrink. Components move closer to failure not because they are broken, but because the environment around them is becoming less forgiving. Engineers can see the trend clearly and can only plan around it, not stop it. Cold also changes how electricity behaves. At extreme temperatures, voltages can drift, timing circuits can slow, and electrical noise can increase. Voyager's computers were built with wide tolerances, which helps them survive these changes, but even they were never tested for conditions like this. Engineers occasionally see strange telemetry, unexpected signal delays, or brief data dropouts. Sometimes these look like serious failures, and then they vanish when temperatures rise slightly due to a change in spacecraft orientation or activity. Cold creates effects that mimic permanent damage, making it harder to tell what is truly breaking and what is simply behaving differently. Thermal stress interacts with radiation damage as well. As temperatures fall, the effects of cosmic radiation on memory and electronics become harder to manage. Bit flips in memory occur more often, and the spacecraft's limited ability to correct errors is stretched. Engineers must constantly determine whether corrupted data is the result of radiation, cold, or a real hardware failure. Each decision matters because the wrong response can waste precious power or push a fragile system past the point of recovery. There is no way to reverse this process. No command from Earth can warm metal that has been cooling for decades. No software update can restore lost heat. Every watt used for heating is a watt taken away from instruments or the transmitter that keeps Voyager in contact with Earth. Engineers do not fix the cold. They manage its consequences, studying temperature trends and deciding which systems must be protected and which can be sacrificed next. The cold does not attack everything at once. It weakens the spacecraft unevenly. A sensor may become unreliable. A voltage line may drift. A mechanism may respond more slowly than it used to. Voyager does not fail in a single dramatic moment. It fades piece by piece as the environment slowly overwhelms systems that were never meant to last this long. None of this was supposed to work. Voyager was designed for a short mission through the outer planets, not for decades in interstellar space. It was not built to survive with heaters shutting down one by one, with components operating far below their rated temperatures, or with materials slowly contracting under relentless cold. Yet the spacecraft is still responding to commands and still transmitting data, even as it continues to cool. The cold is steadily taking control, and Voyager is enduring it for as long as physics allows. Micrometeoroids and dust. What space is doing to Voyager right now? Out where Voyager is traveling, space is not empty, and it is not calm. It is filled with dust grains and tiny particles moving at enormous speeds. These are not rocks you could see with the eye. Many are smaller than grains of sand, some closer to smoke particles, but their speed makes them dangerous. Voyager is moving through interstellar space at tens of thousands of kilometers per hour, and the dust it encounters is moving too. Relative speeds can reach tens of kilometers per second. At those speeds, even a microscopic particle carries enough energy to cause damage. Every time one of these particles strikes Voyager, it hits like a bullet. There is no gentle contact. The particle vaporizes instantly, and a small part of the spacecraft surface vaporizes with it. The impact creates a brief flash of plasma, a tiny cloud of charged particles that lasts for only a fraction of a second. Voyager cannot see these impacts directly, but their effects accumulate over time. Each strike removes an almost invisible amount of material, but over decades those losses add up. Voyager has no shielding against this environment. It was never designed to. Engineers expected it to pass quickly through the outer solar system, not to spend decades moving through regions filled with interstellar dust. Adding shielding would have increased weight, and weight was already tightly limited. Instead, Voyager relies on the simple hope that impacts would be rare enough not to matter during its short planned lifetime. That assumption no longer applies. The spacecraft's antenna, booms, and exposed surfaces are constantly facing this slow erosion. The antenna dish, which is the only reason Voyager can still talk to Earth, is directly exposed to the flow of dust. Each impact slightly roughens its surface. The changes are too small to notice in a single year, but over long periods they can alter how radio waves reflect and focus. Engineers watch signal strength carefully, knowing that even small surface changes can weaken communication over billions of kilometers. Electrical systems are also at risk. When a dust particle hits and creates a plasma discharge, it can briefly spike local electrical fields. Most of the time, Voyager's systems absorb these disturbances without lasting damage. But occasionally, a discharge can induce a small electrical surge. Over time, these surges stress components, weaken insulation, and increase the chance of permanent failure. The spacecraft's wiring was never designed to endure decades of random electrical stress from dust impacts. The long booms that hold instruments like the magnetometer are especially vulnerable. They are thin, exposed, and extend far from the spacecraft body. Each impact slightly weakens their structure. There is no redundancy and no repair option. If a boom were to crack or break, that instrument would be lost instantly. Engineers have no way to prevent this, and no way to detect most damage until it affects data. Interstellar dust also affects thermal behavior. As surfaces erode and change texture, they absorb and radiate heat differently. This alters how Voyager sheds its already limited heat into space. A surface that once reflected energy efficiently may now absorb more cold from the surrounding environment. These changes are subtle, but in a spacecraft operating on the edge of survival, subtle changes matter. The danger is not a single catastrophic impact. The odds of Voyager being destroyed by one large particle are extremely low. The real threat is slow, constant damage. Thousands, possibly millions of tiny impacts over decades wear the spacecraft down in ways engineers cannot fully track. There are no sensors dedicated to monitoring surface erosion. There is no alarm that sounds when a critical threshold is crossed. Damage accumulates silently. Voyager cannot dodge these particles. It has no propulsion system capable of changing course. It cannot rotate to protect one side more than another without risking loss of antenna alignment with Earth. It moves forward on a fixed path, taking whatever space throws at it. Every kilometer traveled adds new impacts, new erosion, and new stress to systems that are already weakened by cold, radiation, and aging electronics. Engineers account for this threat indirectly. When data becomes noisier, when signal strength drops unexpectedly, when an instrument begins behaving strangely, micrometeoroid damage is one of the possibilities they consider, but there is rarely proof. Space does not leave fingerprints. It only leaves effects. This environment will not improve. As Voyager moves deeper into interstellar space, dust density may change, but it will never disappear. There is no safe zone ahead, no quieter region waiting. The spacecraft will continue to be sandblasted by particles moving faster than rifle bullets, with no armor and no way to respond. Voyager survives this not because it is protected, but because it was built simply and strongly enough to tolerate gradual harm. The spacecraft is not resisting damage. It is absorbing it, impact by impact, year after year, as it continues its silent passage through space that is far more active and destructive than it appears. The last signal: how contact ends. Voyager does not send pictures anymore, and it does not send dramatic alarms when something breaks. Everything that still reaches Earth arrives as a faint radio whisper, carried on an X-band signal that has been traveling for more than a day at the speed of light. This signal is not strong, and it never was. Even when Voyager was young, its transmitter was small and weak compared to anything used near Earth. Today, that weakness defines how the mission will end. Voyager's transmitter outputs about 20 watts of power. That is roughly the same as a small household light bulb, and even that comparison is generous because the transmitter cannot use all of that power continuously. The signal leaves the spacecraft through the high-gain antenna, a dish just over 3 meters wide, carefully aimed back toward Earth. That antenna focuses the energy into a narrow beam, because spreading it out would make the signal vanish instantly into space. Even with that focus, the signal spreads as it travels. By the time it reaches Earth, it has expanded to a size larger than our planet. What finally arrives is unimaginably weak. The power received at Earth is less than a billionth of a watt. It is so faint that it does not register as energy in any normal sense. It is detected only because engineers know exactly where to look, exactly what frequency to listen to, and exactly what pattern the signal should follow. Without that knowledge, Voyager would already be silent. The signal does not overpower noise. It barely rises above it. This is where the physics of communication becomes unforgiving. Radio waves weaken with distance according to simple geometry. Double the distance and the signal spreads over 4 times the area. Voyager is now more than 20 billion kilometers away and still moving farther every second. No upgrade on Earth can change that basic rule. Every year, the signal becomes weaker simply because space between Voyager and Earth keeps growing. To hear something this faint, NASA relies on the Deep Space Network. These are not ordinary radio antennas. They are massive, precisely shaped dishes 70 meters wide, placed in carefully chosen locations around the world. One is in California, one in Spain, and one in Australia. Their size is not for show. Bigger antennas collect more signal, and without them, Voyager would have gone silent decades ago. Even so, these antennas operate at the edge of what physics allows. Earth's rotation immediately complicates everything. Any single antenna can only track Voyager for part of the day. When Earth turns and Voyager drops below the horizon, another antenna on the other side of the planet must take over. There are gaps, handoffs, and brief windows where communication is not possible at all. Engineers schedule commands and data returns around these windows with extreme care because every minute of listening time matters. As Voyager's signal weakens, listening becomes harder, not only because the signal fades, but because noise does not. Space is not quiet in radio frequencies. The universe itself glows. There is constant background noise from distant galaxies, from charged particles, and from cosmic radiation. This noise sets a flaw that cannot be removed. You can filter, average, and process signals, but you cannot make the universe stop emitting radio energy. As Voyager fades, its signal sinks closer and closer to that noise floor. The Sun adds another layer of difficulty. When Voyager appears close to the Sun in the sky from Earth's point of view, solar radio emissions interfere directly with communication. During these periods, signal quality drops sharply. Commands may be delayed or avoided entirely. Engineers already plan around these solar interference windows, but as Voyager's signal weakens further, even mild interference becomes enough to drown it out. Inside the Deep Space Network, engineers use extreme signal processing techniques to recover Voyager's data. Bits are repeated, averaged, and reconstructed. Error-correcting codes are applied to detect and fix mistakes caused by noise. These methods allow meaningful data to be extracted even when the signal is barely detectable. But these techniques have limits. When too many bits are corrupted, no amount of processing can recover the original message. Another constraint is time. Voyager's radio signal takes over 20 hours to reach Earth. Commands sent from Earth take just as long to arrive at the spacecraft. This delay means engineers cannot react quickly to problems. If a command is misunderstood or a response is garbled, an entire day can pass before anyone knows. As the signal weakens, the risk of miscommunication increases. Eventually, sending commands may become too risky because the chance of error outweighs the benefit. Power decline makes everything worse. The transmitter itself needs electricity, and that electricity comes from a power system that is slowly failing. Engineers have already reduced transmitter power where possible, and future reductions may be necessary. Each reduction directly weakens the signal. There is no reserve to draw from. Once the power drops below what the transmitter requires, communication ends immediately, without warning. Antenna pointing is another fragile requirement. Voyager must keep its high-gain antenna aimed at Earth with extreme precision. Even a small misalignment spreads the signal enough to make it undetectable. This pointing depends on attitude control thrusters and onboard computers that are themselves aging and losing power. If attitude control weakens, the antenna may drift. The spacecraft might still be alive, still running instruments, but Earth would hear nothing. What makes the end especially quiet is that there is no single failure that causes silence. The last signal does not end with a dramatic event. It fades. Data rates are reduced first. Then only basic telemetry is sent. Then only a carrier signal, a simple tone confirming that Voyager still exists. Eventually, even that tone becomes impossible to distinguish from noise. Engineers may not know the exact moment contact is lost. They will simply notice that nothing recognizable comes back. Even after Earth stops hearing Voyager, the spacecraft will not suddenly shut down. It will continue traveling, systems freezing, power declining, computers running until they cannot. The radio transmitter may still turn on, still try to send a signal, but without enough power or proper pointing, that signal will never be detected. Voyager will be speaking into space, unheard. The Deep Space Network itself has limits that cannot be pushed much further. The antennas are already operating near their maximum sensitivity. Thermal noise in receivers, background radiation, and physical size all set boundaries. Building larger antennas would help, but not enough to reverse decades of signal loss. There is no planned upgrade that will suddenly make Voyager loud again. When contact finally ends, it will be because physics has won. Distance, noise, power loss, and time will combine to erase the signal. Not in a moment, but gradually, as engineers exhaust every trick available to listen just a little longer. The last signal will not be marked by an alarm or a final message. It will be marked by silence where something faint once was. A silence caused not by failure, but by the simple fact that Voyager has gone too far and Earth can no longer hear it. Voyager will not end with a burst, a flash, or a dramatic final transmission. There will be no last words, no warning tone, and no clear moment anyone can point to and say this is when it died. The way Voyager goes silent is quieter than that, and far more unforgiving. It ends not because something explodes, but because one small requirement for communication is no longer met, and once that happens, there is no path back. The most likely way silence begins is simple power loss. Voyager's transmitter needs a minimum amount of electricity to function at all. Not to function well, not to send data clearly, but just to turn on and produce a radio signal. As the radioactive fuel inside Voyager's power system continues to decay, the available electrical power drops every year. Engineers already run the spacecraft with almost nothing to spare. Heaters are shut down, instruments are sacrificed, and power is routed only to systems that are absolutely necessary. Eventually, the power level will fall below what the transmitter requires. When that happens, the transmitter does not weaken gradually. It stops. One moment it can generate a signal, the next moment it cannot. There is no recovery from that. No command from Earth can add power that no longer exists. Another path to silence comes from attitude control failure. Voyager must keep its high-gain antenna pointed toward Earth with extreme precision. The beam it sends is narrow, and even a small drift spreads the signal so much that it disappears into background noise. This pointing depends on tiny thrusters, sensors, and onboard computers working together. These systems are old, exposed to radiation, and increasingly affected by cold. If a thruster fails, if fuel lines freeze, or if control logic becomes unstable, the spacecraft can begin to rotate slowly. It may still be alive internally, still powered, still running code, but if the antenna is no longer aimed correctly, Earth hears nothing. From the ground, this looks exactly the same as total failure. Silence does not mean Voyager is dead, it means Voyager is no longer facing us. The third scenario is the most unpredictable and the hardest to prevent. Voyager's computers are based on 1970s technology, designed to be reliable but never meant to run for half a century in deep space. Radiation can flip memory bits. Power drops can cause timing errors. Extreme cold can affect logic circuits. Occasionally, the computer may reset itself. In most cases, it recovers and resumes operation. But one day, a reset may happen at the wrong moment, corrupting memory or trapping the system in a state it cannot escape. If the computer fails to reboot correctly, it may never re-establish communication routines. The transmitter might still have power. The antenna might still be aligned. But without the computer telling the radio what to send, Voyager becomes silent. None of these scenarios involve destruction. Nothing shatters, nothing burns. Voyager does not break apart or shut down in a clean sequence. It simply stops being heard. Engineers on Earth will keep listening, using the largest antennas available, filtering noise, and checking every possible frequency and signal pattern. At first, they may think the signal is just weak or temporarily lost. Days may pass, then weeks. Commands will be sent anyway, just in case Voyager can still hear Earth, even if Earth cannot hear Voyager. There will be no reply. What makes this ending so stark is that it offers no closure. There is no confirmation of what failed. Power loss, misalignment, or computer failure all produce the same result at Earth. Silence. The spacecraft could still be drifting, systems slowly freezing, transmitter occasionally attempting to turn on, antenna sweeping past Earth's position without ever locking on. Or it could be completely inert. From Earth, there is no difference. Voyager was never designed to announce its own death. It was designed to send data as long as it could, and then stop when physics no longer allowed it. When that happens, the end will not be obvious. The last signal will not arrive labeled as the last signal. Engineers will only know in hindsight, when weeks turn into months and nothing ever comes back. There will be no final message because Voyager cannot know it is dying. It does not have awareness of its own condition. It does not prepare goodbyes. It simply follows instructions and physics until one requirement for communication is no longer met. At that moment, contact ends, not with drama, but with absence. Silence replaces a signal that had been growing weaker for decades, and space continues on exactly as it was before, with Voyager still moving forward, unheard. After silence, Voyager's physical fate. When Voyager finally goes silent, nothing dramatic happens in space. There is no instant change, no visible event, no sudden collapse. From Earth, the mission is over the moment the signal disappears, but for the spacecraft itself, the transition is slow and quiet. Voyager does not know it has died. It simply stops doing the few things that made it visible to us. The transmitter no longer turns on, the antenna no longer matters, and commands from Earth arrive to a spacecraft that can no longer respond. What remains is a physical object drifting through interstellar space, still obeying the same laws of physics it always has. The first real change after silence is that Voyager becomes fully inert. While contact existed, at least some systems were active. A computer was running, a transmitter was switching on and off, and a few instruments were still powered. Once communication ends, power continues to fall, and eventually there is not enough electricity to sustain even the most basic internal activity. The onboard computers stop executing instructions. Memory contents fade or become meaningless. Clocks stop ticking. Voyager is no longer a machine in operation. It becomes a frozen artifact. Heat inside the spacecraft stops circulating almost entirely. While Voyager was alive, even minimal electrical activity produced waste heat that helped keep internal components above extreme cold. After silence, that heat source vanishes. There is no redistribution of warmth from one part of the spacecraft to another. Each component cools on its own, radiating what little heat it has into space. Temperatures drop steadily, not in minutes or hours, but over months and years, until everything approaches the background temperature of interstellar space. Electronics freeze permanently, not metaphorically but physically. Metals contract to their smallest stable dimensions. Solder joints lock into place. Any remaining lubricants thicken to the point where movement becomes impossible. Plastic insulation becomes brittle. Capacitors, resistors, and integrated circuits settle into a state where they will never function again. Even if power somehow returned, the spacecraft could not wake back up. This is not a shutdown that can be reversed. It is a physical end state. Voyager's power source does not suddenly stop working. The radioisotope thermoelectric generators continue to decay quietly. Plutonium-238 does not care whether the spacecraft is alive or dead. It keeps releasing heat as it decays year after year. But by this point, the heat output is extremely small. There is not enough electrical conversion happening to power anything meaningful. The remaining heat slowly leaks into space, providing a tiny warmth that delays full thermal equilibrium, but does not prevent it. Voyager becomes cold all the same. Once inert, Voyager is no longer actively affected by most of the things that destroy objects on Earth. There is no air in interstellar space, so there is no atmospheric erosion. Nothing blows against its surfaces. There is no oxygen to cause rust, no moisture to trigger corrosion, and no biological life to consume materials. Bacteria cannot survive here. Fungi cannot grow. Decay, as we know it, does not exist. Voyager enters an environment that is almost perfectly preserving. Structurally, the spacecraft remains intact. Its aluminum frame does not rot. Its antenna does not crumble. The long instrument booms stay extended. Fasteners remain locked in place. Paint does not peel. Labels and markings fade only very slowly, altered mainly by radiation rather than wear. Even the golden record, mounted to the side of the spacecraft, remains physically unchanged, protected by its cover, drifting through darkness. Micrometeoroid impacts continue, but their effect is gradual. Tiny particles strike Voyager at high speed, vaporizing on contact and slowly eroding surfaces. This does not break the spacecraft apart. It acts like extremely slow sandblasting. Over millions of years, edges become smoother, surfaces become rougher, and thin structures may weaken. But this process is measured in geological time, not human time. Voyager will not fragment anytime soon. Radiation continues to pass through the spacecraft. High-energy particles strike electronics, memory chips, and metal structures. With no power and no data to protect, these impacts no longer matter in an operational sense. They do not cause failures because there is nothing left to fail. Radiation damage simply accumulates silently, altering atomic structures, changing material properties slightly over immense spans of time. Voyager's trajectory remains stable. There is nothing to slow it down in any meaningful way. Interstellar space is so empty that even over millions of years, drag is effectively zero. The spacecraft continues moving on the same path it has been on since it left the solar system. Gravity from stars it passes will bend that path slightly, but Voyager is not headed for any star in the foreseeable future. It drifts, unchanged, carrying its shape and structure across vast distances. Because there is no atmosphere, no weather, and no chemical erosion, Voyager remains recognizable for an extraordinarily long time. If another civilization were to encounter it millions of years from now, they would not find debris. They would find a spacecraft. Dented, eroded, radiation scarred, but intact. Bolts still in place. Antenna still attached. Record still mounted. Nothing consumes Voyager. Nothing buries it. Nothing breaks it down into raw material. The spacecraft becomes one of the most durable objects humanity has ever made, not because it was designed for eternity, but because space itself is a preserving environment. Voyager survives not by resisting destruction, but by being removed from the conditions that cause destruction at all. Long after its power source has faded to near nothing, long after its electronics have become inert, Voyager continues to exist as a physical object. It does not transmit. It does not sense, it does not respond, but it remains, moving through interstellar space exactly as physics dictates, unchanged in purpose because it no longer has one, unchanged in form because nothing is there to take it apart. Silence does not end Voyager's journey, it only ends our ability to witness it. Voyager is not stopping when it goes silent. Silence only ends communication, not motion. The spacecraft keeps moving because nothing in space is there to stop it. There is no air, no friction, no drag. Voyager left the solar system with speed, and that speed is preserved. Right now, Voyager 1 is moving at roughly 17 kilometers per second relative to the Sun. That number sounds small until it is stretched across time. 17 kilometers every second becomes more than 1 billion kilometers every year. Over thousands of years, that motion carries Voyager across distances that completely redefine what far means. Voyager is no longer bound to the Sun. It escaped the Sun's gravity when it crossed the heliopause and continued outward with enough velocity to never fall back. From that moment on, its motion stopped being a solar orbit and became a galactic one. The spacecraft is now a free object inside the Milky Way, moving on a path shaped by the combined gravity of the galaxy itself rather than any single star. Its trajectory is not aimed at a destination. It is a straight-line motion modified very slowly by forces that act over tens of thousands to millions of years. One of the few close encounters Voyager will ever have is with a star called Gliese 445. This is not a dramatic flyby in the way science fiction imagines it. Voyager will not enter the star's system. It will not pass near any planets. It will not slow down or change direction sharply. In about 40,000 years, Voyager 1 will pass within roughly 1.6 light-years of Gliese 445. That distance is still enormous. It is closer than Voyager will come to almost any other star, but it is not close enough to be captured. Gravity at that range produces only a gentle tug, barely bending Voyager's path. That small bend matters only when viewed over extreme time. Gravitational forces in the galaxy act like slow hands. nudging objects instead of grabbing them. As Voyager travels, passing stars apply tiny pulls. Most of the time, these forces cancel out. Occasionally, a nearby star causes a slightly stronger deflection. None of these interactions are sudden. There are no sharp turns, no violent slingshots. Voyager's path curves so gradually that it would appear straight on any human timescale. The galaxy itself also exerts influence. The Milky Way is not a uniform environment. Its mass is concentrated in a disk, with stars, gas, and dark matter shaping a gravitational field that everything inside it responds to. Voyager is now part of that system. As it moves, galactic tides slowly alter its trajectory, guiding it into a long, looping orbit around the center of the Milky Way. This orbit is not neat or circular. It is stretched, uneven, and shaped by encounters that occur over millions of years. What Voyager will never do is enter another star system in any meaningful way. The space between stars is vast beyond intuition. Even though stars move and Voyager moves, the odds of a direct encounter are extremely small. Voyager's path does not intersect any known planetary systems. Over the lifetime of the galaxy, it may pass closer to some stars than others, but capture requires losing energy, and there is nothing available to take that energy away. Without friction or collisions, Voyager cannot be pulled into orbit around a star. As time stretches forward, Voyager becomes just another small object orbiting the galaxy. Its speed relative to nearby stars changes as those stars move in their own orbits. From one frame of reference, Voyager appears fast. From another, it appears slow. But the overall motion continues. It completes vast arcs around the galactic center, taking hundreds of millions of years for each full circuit. Through all of this, Voyager remains physically unchanged in purpose. It is no longer a spacecraft performing a mission. It is a manufactured object following celestial mechanics. Nothing marks these moments. There is no record of Voyager passing Gliese 445. No signal announces it. The event happens quietly, unnoticed, just another alignment in a galaxy full of them. Voyager does not react. It does not adjust course. It simply continues, carrying its shape, its mass, and its velocity forward. Over very long timescales, gravitational perturbations accumulate. Small deflections add together. Voyager's path becomes less predictable in detail, though its general fate remains clear. It stays inside the Milky Way. It does not escape the galaxy. The galaxy's gravity is far stronger than the Sun's ever was at Voyager's distance. Voyager is now bound to the Milky Way in the same way stars are, tracing long, slow paths around its center. Eventually, long after the spacecraft has gone cold, long after its power source has decayed to insignificance, Voyager becomes indistinguishable from other small objects drifting between stars. It does not decay. It does not dissolve. It simply exists. Its materials persist. Its structure holds. Its motion continues. Long after Earth has changed beyond recognition, long after human civilizations may have ended or transformed, Voyager remains physically present. It does not orbit Earth. It does not orbit the Sun. It orbits the galaxy itself, moving endlessly through interstellar space as a silent artifact, not transmitting, not observing, not responding, but still obeying gravity, still tracing a path written by physics alone.